So let us in the last discussion we were actually talking about this Wick's theorem. So let us continue with that. So what we saw was the following, that if we have a time ordered product of a string of operators, say, and we want to, our aim is to calculate this thing, this object, because as I mentioned, well, our aim is to calculate this thing. For the full interacting theory, we want to calculate such an object, and we have seen an expression of a vacuum expectation value of a product of the product of two operators, two field operators in the Heisenberg representation, and the vacuum expectation value has been taken in the full interacting vacuum. We have seen how we can relate it to the vacuum expectation value of the interacting field operators, which basically involved by the free Hamiltonian in the vacuum of the free theory. So we have seen that expression. So our goal is therefore to calculate objects like this, where these are basically interacting field operators, that is operators in the interaction representation, and therefore they evolve by the free Hamiltonian, and we want to calculate the vacuum expectation value where the vacuum is that of the free theory. So we want to calculate expressions of this form, but it turns out that even calculating this is very for this vacuum of the free theory is a difficult task. But we know that identically a normal order product of the same string of operators A, B, C is zero. We already know this. Therefore, what we try to do is to express this thing in terms of this. So let's see how can we achieve this thing. So in the previous lecture, we were looking at A, B, and we wrote down A as A plus A minus, and similarly for B, A, B, and we wrote down A as A plus A minus, and similarly for B, where A plus stands for the annihilation part, A minus stands for the creation part of the operator, and then if you just expand this will be B plus B minus. So now we just multiply this out. So this is A plus B plus. So I'm just repeating the part that we were discussing. So let me just do it once more. So this will be A minus B minus. And now, if I take a normal order of this, then by definition, the normal order, this will remain the same. This will be A plus B plus plus. This is already in the normal order form because this is the creation operator which is sitting on the left of the annihilation operator. Therefore, this is normal order. This is not normal order. So if you normal order this is B minus B plus. And this is already in the normal order form because both are creation operators. And now what we do is just subtract NAB from AB. So if you subtract, you can immediately see that this cancels with this cancels with this, and this cancels with this. Therefore, what we have is A plus B minus of B minus A plus, so it is basically a commutator. This is what we get. And you can just write this expression in the following form. If I just put arguments AX BY minus N AX BY, I'm just putting the space-time argument X and Y. So this will just be equal to the commutator of A plus with X and B minus with Y. So this is the result that we have. Okay.
Sir, The normal ordering you have used here, I mean, that is for bosonic particles.
Yeah, let us do it for bosonic for the time being.
Okay.
Okay. Let us do it for bosons. You are correct. Let us do it for bosons. For fermions, you are right. You have to take care of the sign and everything because you need to take care of the signs. But that is not a problem. You can just generalize. You can do it for fermions also. But you are, as you mentioned, let us consider these operators to be bosonic. So let me write it down on top. These are for bosonic operators. Similarly, now you can show. Let me write down what BA is. So what is BA? BA is a similar calculation. B plus B minus A plus A minus, and this is equal to B plus A plus B minus A plus B plus A minus plus B minus A minus. And if I normal order this, this will give me, see, this is already in the normal order form. So you can write it in this way, plus it's also normal order form. This is not in the normal order form, therefore this is A minus B plus, and therefore, and this is A minus B minus. So this is what we have. And from here, you can also see that since A plus and B plus, they commute with each other, or the operators AB commute with each other, so you can put it over here. This thing is basically what? B minus A plus. So that is here. That is this operator. A minus B plus. A minus B plus is this operator. And B minus A minus, you can put A minus on here. Therefore, this B minus A minus is the same as A minus B minus. So this is basically nothing but normal order of AB. So normal order of BA is basically normal order of AB. Now we just subtract this from this. So what we will have is B. Similar, just as in the previous calculation, you can see that if you subtract, this will cancel with this. B minus A plus, A minus, this will cancel with this. And then we'll have what? B minus A plus. So this will cancel with this. And therefore, you can now write this thing as By Ax. If you just put in arguments, then this will be By Ax minus normal order of, since normal order of BA is the same as normal order of AB, therefore this is just Ax By. And write as you want, as you wish. You can also write normal order of By Ax because both are same. And this is equal to nothing but the commutator. See, this term and this term, this gives you a commutator, and this will be basically B plus Y A minus X commutator. So you have this result. So what we have is, we have this result and we have this result. So what we need to do now is to combine these two results. So let me write it here. We have Ax By minus N Ax By, that is equal to A plus X B minus Y commutator. This is one of the results, and we have By. So we can see By Ax minus normal order of equal to the commutator of b plus y a minus x. So this is what we have. So these are the two results that we have just now derived, and therefore you can now write this result in a combined form. You can write it up in a combined form. So what we can do is we can write these two results as time order product of Ax dy minus normal order product of Ax dy. So when x is greater than y, then Ax will be on the left hand side of dy, right? When x naught is greater than y naught, when the two times this time is greater than this time, then Ax will be on the left hand side of dy, and then it will be this commutator. So the result is a plus x x naught greater than y naught, and if y naught is greater than x naught, then you will have by sitting on the left of ax, and the result will be b plus y a minus x for x naught less than y. So you can write it in this way. We have combined the two results. You can actually see the full board now here. And let me just erase this part.
Sir,
Okay. Yes.
sir, minus sign denotes the creation operator part, right, sir?
Creation operator. Yes.
Okay.
Minus denotes the creation part, plus denotes the annihilation part.
Okay, sir.
Okay. So therefore, you can actually write this result in a very nice form. You can write it in this way: Ax by. So just look at that result, and you can write it here. I will just zoom this part in a moment. Just wait for 2 minutes. Ax by. So when you subtract the normal order form from the time order form, you can write this as theta x naught minus y naught. Then we have a plus x commutator with b minus y plus theta this is what. So you can write this result, the result that I wrote down on the other side, on the right side of the board, in this way. So this is the thing that I wrote down. And then what we can do is we can take a vacuum expectation value. So this will be our vacuum expectation value. we know that the vacuum expectation value of the normal order product of these any string of operators is basically 0. So this term is gone, and therefore the vacuum expectation value, therefore what we have is Ax dy vacuum expectation value of the time order product of two operators. This is basically theta x naught minus y naught. Then you have this vacuum expectation value of the commutator a plus x b minus y plus theta y naught x naught, the commutator of e plus y b minus x. So this is your final result. This is the general result that we have. Okay. Is this fine?
Yes.
Okay. Now let us just take it for a simple case. What this formula gives us. You can just take Ax to be equal to phi of x, and similarly you can take By as phi of y. Okay, so this is the real scalar field, and you know that this is phi plus x plus phi minus x. It's the annihilation part, it's the creation part, and you know what they are. And if you just substitute it over here, so in the phi plus x, what will you have? You will have an a, right? The ak, the annihilation operator, and there will be an integral, normalization factor, e to the power of minus I k dot x, and so on. So this is what you will have, or you can also, when you write this as ak, you can actually put a summation over k, and then put 1 by 2 omega k volume v square root ak e to the power of minus I k dot x. So this is your phi plus x. And similarly, you have a phi minus x which contains a plus, a dagger. And therefore, you just see here, this will be ak and this will be a dagger k, right? With a different k prime, a dagger k prime. And you know that this commutator is delta k prime. You just calculate it, you just put it there, and you will also do the same thing for here, for this thing. And then if you calculate this, then you will end up with the result that we have already derived, that phi x, phi y is nothing but I delta f x minus y. So this is just a check that you have done all these formulas are correct or not. So you can check this. You can now take A to be a complex scalar field also. So this will be phi, and this will be B will be appropriately. You just take B to be By to be phi y. So these are complex scalar fields, and then you know what phi plus is. Phi plus has a, and but phi minus is not a dagger. It is basically B dagger. And similarly, B is also phi. So for that also you have a and B dagger part, and you just put it there, and you will see, and just work it out and see what happens for complex scalar field. And so these are bosonic fields. You can do the same thing for electromagnetic field, because that is also a bosonic field. For fermionic fields, you have to be a little bit careful. You just try to figure it out, or else I will, when I discuss fermions, I will again look at this part and tell you what happens there. So this is basically what we have done is we have looked at the Wick's theorem for a string of two operators, where we have two operators. But let me do one thing one more thing. We have already seen that the time ordered product of two operators minus the normal order product of two operators is basically a commutator. And commutator is a number, right? It is a number, it is a C number. So in general, what we can do, we can define some object like this, which is basically nothing but this quantity. Okay? So let us define this quantity. A quantity where you have a line like this, which is basically the difference between these two quantities. And this quantity is said to be a contraction. A contraction of two operators, of a pair of operators. And what is a contraction of a pair of operators is basically a commutator in this case. For any contraction, time order product and this contraction is a commutator and therefore it is a C number. And now you just take a vacuum expectation value of this contraction. The vacuum expectation value of this contraction is basically time order product. I'm not writing, by the way, the arguments. The arguments are also important, but let me just keep it for the moment. So this will be this minus the vacuum expectation value of the normal order product, but that is 0. Okay. So what we have is that the contraction is this contraction. Since this is a number, you can take it out. Therefore, this is nothing but this. Okay. And now what we can do is we can write down this time order product of AB as the normal order product of AB plus AB contraction. So this is AB contraction. Okay. So you can write this in a compact form also. You can write this as normal order form of AB plus you can put this inside the normal order form. It doesn't matter because this is already a number. So this is actually, so you can see that the time order product of a pair of operators is basically the normal order form of a pair of operators plus this. Well, you can take this outside also of the normal order form, or you can just put it inside the normal order form. Because this is a number. This contraction is a number because it is a commutator. Therefore, you can put it wherever you like. This form is said to be the Weeks theorem. This is the Weeks theorem. We have just shown it for a pair of operators. You can prove it in general for a string of n operators. In general, you can prove it. For example, if you take, say, 3 operators or 4 operators, say, then what will happen? So let me write it down. Let me write this result. Suppose I have A, B, C, like this, a string of operators. Then this will be nothing but this is the normal order form of A, B, C, plus all possible contractions of ABC. So this is Z plus all possible contractions of ABC. So let us see what this means. I have already mentioned this before, but I would like, at this point, I would like to mention this once more, that this Week's theorem works only for free fields. That is, the fields which are in the interaction picture or the Dirac picture. It does not work for the fields in the Heisenberg representation, or by Heisenberg representation I mean that these are the fields which appear in the which evolve, or rather evolve via the full interacting Hamiltonian. That is the better way to say. So this works only for free fields, not for interacting fields. But you know how to write down a vacuum expectation value involving interacting fields. By interacting fields, I do not mean fields in the interaction picture. Fields in the interaction picture are free fields. They evolve via the free Hamiltonian. The interacting fields are fields in the Heisenberg representation which evolve via the full Hamiltonian. So we know how to write down a vacuum expectation value of a string of a time ordered product of at least a pair of operators which are interacting fields. We know how to write it down in terms of free fields. Once you write that formula down, now you can apply the Week's theorem. So here comes the use of the Week's theorem. We will see how to apply the Week's theorem. So you have to just wait for another couple of classes, and then we can see how we can apply this. So this is the most general form of the Week's theorem, and we can actually prove it by the method of mathematical induction. You can try. We have proved it for 2 operators. Now you do it for 3 operators. Then you just assume that the result holds for a string of n operators, and then you show if the result holds for a string of n operators, it will also hold for a string of n plus 1 operators. So if you can prove it, then since it holds for n is equal to 2, it will hold for n is equal to 3. N is equal to 1 is trivial. There is nothing to prove. Since it holds for n is equal to 2, it will hold for n is equal to 3, and so on. So you can. This is the method of mathematical or principle of mathematical induction. You can prove it by that method. So let us just take a very simple case and see how does this work. Let us consider a product of a time order product of 4 operators. So this will be what? This will be equal to n a b c d plus all possible contractions. So what we can do is, so this is the normal order form. So what we will have is the following. You can take this contraction AB, just take a pair at a time. So this will be AB, and then leave the other 2, NCB, plus. You can now take AB, you can now take AC, contraction, then normal order form of BD. You can then take AB, normal order form of BC. So this exhausts everything with A, with B, A with C, A with D. Now you take B. So B with A is already taken care of. So that will be overcounting. You don't need to do it. So you need to take B with C. So if you take BC, then you will have normal order form of AB plus B with D, contraction. All these contractions, just recall that these are numbers. So you can just take it outside the normal order form. B with D. So what remains is A with AC. So that is inside the normal order. So now plus B is done. So now you take C. So you see that C with A is already taken care of. So you don't need to take it. C with B is also taken care of. Don't need to take it. C with D is not taken care of. C with D is this. Then you have normal order form of AB. Right? So this is all possible permutations where you take the contraction of a pair of operators. So this is it. So there are how many terms here? 1, 2, 3, 4, 5, 6. Okay. Now what we can do is, so let me just group these terms like this. Is this clear? Are you okay with it?
Yes, sir.
Good. Now you just take two pairs at a time, but two pairs taking two pairs will exhaust the full thing. So you will have no more terms other than that. So what you can do is you can take AB. So this will be AB, and then the only thing that remains is CD plus. Then you can take A with C. Only thing that remains is B with D. And then the last term, A with D. Only thing that remains is B with C. This exhausts everything. Okay? So this is the time ordered, the expansion of the time ordered product of a string of 4 operators. This is the full expansion. And you can see what happens, what will happen if you take a vacuum expectation value. So this will be a vacuum expectation value of the full thing, right? So if you take a vacuum expectation value, you know that this term will be 0. No. Normal order vacuum expectation value of a normal order product of a string of operators is 0. Identically 0. Similarly, all these terms are 0. This is 0. This is 0. This is 0. 0. Everything vanishes. This is also 0. The only term that remains is this. And these are what? These are basically commutators. But you know what these commutators are. A pair, if you take the vacuum expectation value of a pair of the time ordered product of a pair of a product of operators. So what we have seen from this expression is that if you take a vacuum expectation value of the time ordered product of a pair of operators, it is basically nothing but this contraction. And the contraction is nothing but the propagator. So all these are free propagators. This is a propagator, this contraction is a propagator. So all these are free propagators. So it is a multiplication of the propagators to take the vacuum expectation value of a string of operators. Obviously, these operators are in the interaction picture. So these are free field operators. So you may try and see what will happen. How to write down ABC. You can try this also. Please try it and see what happens. So do you have any questions at this point? Please, I can start a new thing. I can show you another application of the Weeks theorem, and also the formula, a combined application of the formula that I proved in a couple of lectures back, and also the application of Weeks theorem. I can start doing that, but before that, I would like to take up some questions. It is a good point or to pause at this point, because we have almost all the machinery that we need to discuss interacting fields. One more thing I have to discuss, but I will do that later. So please ask questions at this point.
Sir, this is valid for the Dirac picture only.
You should not say that this is valid in the Dirac picture. By your question, what I'm understanding is the following: that you have certain doubt that this works in the Dirac picture and this will not work in the Heisenberg picture. This sort of a question is arising in your mind, right?
Yes, sir.
That this is what in the Dirac picture, will this work in the Heisenberg picture? It is not about that. This is a way to work with interacting fields.
Okay.
This is a way to work with interacting fields. Why? Because as I mentioned to you earlier, what I mentioned is the following: that You just recall that the field in the Heisenberg picture that basically is evolving via the full Hamiltonian or full interacting Hamiltonian, which is at time t is equal to 0. So what we are considering is that the full Hamiltonian is time independent and it is equal to h naught plus v, where v is the interacting part. Okay. Now, given a field configuration at time t is equal to 0, at some position x vector say, so this field this field can evolve by the full Hamiltonian h, and you will get phi tx, and you can also define a new field operator which evolves via the free Hamiltonian h naught. That field we call the field to be in the interaction picture or the Dirac picture. It turns out that when you are discussing interactions, when you want to discuss interactions, it turns out that if you have to set up the formalism in such a way that if you work in this picture, it turns out that things become simpler. You can write down good mathematical expressions. If you could have said that, okay, no, I will not work in the interaction picture or the Dirac picture. I will just straight away work in the Heisenberg picture. But you can try and do it yourself, but you will find that things become extremely difficult. Okay.
Okay.
You will not be able to solve you will not be able to write down neat mathematical expressions in the Heisenberg representation. So it is, but what you just recall the formula that we have derived a couple of lectures back, or maybe in the previous lecture. So if you recall the formula, there you will see that our interest is to compute a quantity which is the vacuum expectation value of the time ordered product of two field operators which are in the Heisenberg representation. Those are the actual fields which capture the effect of interactions. That is what you want to find. Phi x and phi y, these are fields in the Heisenberg representation because they evolve via the full Hamiltonian of the theory. That is what you want to find. And what more, you want to find the time ordered product of those fields and the vacuum expectation value. So you want particles to move in the interacting vacuum. That is the state of minimum energy for the full theory. That is the object of interest that you want to calculate. But you cannot calculate it in the Heisenberg picture. That is the thing. You will not be able to write down an expression for it if you work with the fields phi and the interacting field vacuum or interacting theory vacuum omega, because you neither know what omega is and you neither know what phi is. But what you know is you know the free theory vacuum ket 0, that you know, and you also know what the free interacting the free fields are. Since you know the free fields because they are evolving via the free theory Hamiltonian, and when I say that you know it, I mean that you know their mode expansions, you know their Fourier expansions, normal mode expansion. You know what phi naughts are. So if you know that, and if you know the free theory vacuum, you can calculate the vacuum expectation value of the time ordered product of two free fields, and that we have done in one of the discussions, and we have shown that that is equal to the propagator, free propagator. Now what you are trying to do is trying to calculate the interacting field propagator in terms of the free field operator, because interaction part you treat it as a perturbation. So we are doing perturbative field theory. We are trying to do perturbative field theory. You have an interaction which has some interaction strength, some coupling constant, and you assume what we do standard in quantum mechanics. This is standard that you assume that the perturbation is small. So if you assume that the perturbation is small, then the correction. So then what you can do is that you can write down the full propagator of the theory, of the full interacting theory, as the free propagator, and then correction terms. So that is why we are trying to write down everything in terms of free fields, which you know. The results there are known. And once you just need to write down those results, and then correction terms will also come, and they will be also in terms of free fields, which you know. So this is the philosophy. And what is the picture where you can work with free fields? It is the Dirac picture or the interaction picture. I hope this is clear now. So
Yes,
please
sir.
keep this in mind, and we will in the next discussion we will see another application of Weeks theory. See, our imperturbability field theory, our main thing is to see applications of this Weeks theorem and the formula that we have derived a couple of lectures back. So we'll see how things work with these things. Okay. Bolo.
I have a doubt. Actually, the decomposition that we have done, that an operator equal to a plus plus a minus.
Huh.
So can we say that the a plus corresponds to the positive energy part of the field operator and a
A
minus to
plus.
the negative energy?
Actually, that is what we have done, no? Because A plus is the annihilation part. A
Yes.
plus, if you just write down the mode expansion, I just wrote it down the board. You will have a summation over k 1 by 2 that square root normalization factor ak e to the power of minus ik dot x.
Yes.
This full thing I am calling it to be phi plus.
Yes. Okay. So I am saying that it we can think of it that it corresponds to the positive energy part of the field operator and the a
Yes, yes,
minus
you
corresponds to
can
the
think.
negative energy.
Yes, yes, obviously, sure.
Okay.
Okay. So let us stop here for today.